that you all are having a good start to your week so far. So today we're going to talk about SN2 and E1 reactions with alcohols. Last Friday, we talked about various reactions with alcohols, and now we're going to talk about how they can play in to some of the reaction mechanisms that we've learned a little bit earlier this summer. Namely, we're going to talk about how to convert alcohols into good leaving groups. There are two different methods to do this, one of which is to protonate the alcohol, and the other is to use a step known as tosylation or another similar step known as mesylation. So let's go ahead and get started. So the key reason, or I guess the key takeaway from lecture today, is that in Chem 3570, alcohols are not considered to be good leaving groups. And since that's the case in 3570, we will abide by this in our course as well. This is because OH minus, if you remember from our discussion on nucleophiles, this is a pretty good nucleophile because it is unstable or fairly unstable. You can see that the oxygen has a negative charge. And if a molecule is a good nucleophile, it can't also be a good leaving group, because if you also remember, the best leaving groups are stable with a negative charge, while the best nucleophiles are unstable with a negative charge. So therefore, just kicking an alcohol group off a molecule is not a very feasible step for our course and for Orgo 1. So we're going to discuss two different ways that we can convert the alcohol into a better leaving group. And I'm going to talk about the first one of those. That's to protonate the alcohol so that it's a little bit more stable when you try to get it to leave the molecule. So we're going to talk about a specific example reaction where you have an alcohol and an acid. Bear in mind that this X just stands for any halogen. So this acid could be HBr, HCl, HI, but not HF, because if you remember, fluorine is a pretty poor nucleophile. So any of these three, where X stands for the Br, the chlorine, or the iodine. Now, the basic the overview of this reaction is that we're going to do an SN2 reaction by protonating the alcohol first, and then we're going to attack it using the weak conjugate base of this acid. So I'm going to go ahead here and show how the reaction mechanism works. I'm going to use HBr in this example, and I'm going to draw the lone pair on the oxygen for the alcohol group. And I'll draw an arrow where this lone pair actually will go and grab the hydrogen from our acid. And then, as you have seen in other mechanisms for this course, the bromine takes the electrons from the bond between the hydrogen and the bromine. So this step should be somewhat familiar. After we take the hydrogen, we are left with this molecule here, where we have our alcohol group that has two hydrogens. If we were to do a quick formal charge calculation, we would see that this oxygen, which has 3 bonds and 1 lone pair, it now has a positive charge. And we also have our bromine that has a negative charge. I'm going to move this down here, actually. Now, if you compare this alcohol with the 2 hydrogens and the positive charge to this alcohol that just has the 1 hydrogen and the 2 lone pairs, this is not a very good leaving group, while this group is an extremely good leaving group. This is because if we kick the oxygen with the 2 hydrogens off the molecule, we're going to get something that's neutral instead of something that's negatively charged. So let's show our Br minus. This works as the nucleophile to do a backside attack and force this water molecule to leave. And our product what you would expect for a substitution product. Instead of an alcohol, we have a bromine, or I guess I should say instead of an OH2 plus, we have a bromine. And we also have our neutral molecule of water, which, as I am sure you would expect, is pretty stable hanging out by itself. So are there any questions about this mechanism? It doesn't look like there are any questions, so I'm going to go ahead and move on. So now we're going to talk about a similar reaction. This specific reaction uses the E1 mechanism, and it features an alcohol with a strong acid. Here we're going to use some H2SO4. And the idea is pretty similar to our last reaction. We're going to protonate the alcohol group to create a better leaving group. And then we're going to have the attached OH2 plus leave, and then we're going to do an E1 reaction. So I'm going to go ahead and draw out the H2SO4. Which is drawn a bit differently in organic chemistry than in general chemistry, as you can tell by all the bonds around the sulfur. Anyhow, just as we did last time, I'll draw the lone pairs around the oxygen on the alcohol group, and we will go ahead and attack the hydrogen on the H2SO4. And just like last time, this oxygen will go ahead and take the electrons in this bond between the oxygen and the hydrogen. So what we are left with is a molecule that looks kind of like this, where instead of an alcohol with one hydrogen, we have an OH2 with two hydrogens, positive charge, and one lone pair instead of two lone pairs. As you'll probably recognize from last time, this OH2 plus is a very good leaving group. So our next step in an E1 reaction, the leaving group leaves. This leaving group is such a great leaving group that it can just float off the molecule without needing a backside attack or anything like that. And we are left with our carbocation. It's important to note that because this reaction uses a carbocation, you wouldn't really be able to do the specific mechanism with the H2SO4 if you had like a primary substrate, just because, as I'm sure you remember from before, secondary carbocations are good, tertiary carbocations are even better, but primary and methyl carbocations are not very stable. So keep that in mind. Now that we have our carbocation, we can perform our E1 reaction. We're going to use HSO4 minus as our base. As you probably remember from Chem 2080, H2SO4 is a polyprotic acid, meaning that it can give off multiple hydrogens. However, as I'm sure you also remember, the HSO4 minus can function as either an acid or a base. And here it is functioning as a base. I'm going to take this hydrogen, and we're going to end up with our double bond between them right there. And of course, our neutral water molecule from before. Now, I'm sure some people might be wondering why this reaction proceeds specifically as an E1 reaction and why not an E2 reaction or something else like that. Well, if we think about it, whenever we have a strong acid and we give away a hydrogen, we end up with a weak base. And if we remember from before, E1 reactions can proceed with a weak base, but you need a pretty strong base in order to pull off an E2 reaction. So that's why this mechanism is specifically E1. Are there any other questions that we can answer? Also, feel free to let me know if my internet is lagging or anything like that, because I could always like repeat something or try to go a little bit slower. Okay, so there don't appear to be any questions, and we are going to go ahead and move on to an example problem where we will get to practice what we've just learned. This is an example of a synthesis problem, which is my favorite type of problem in all of Orgo, because it's kind of like a puzzle. If you didn't know, basically you have your starting material and you have your final product, and it's your job to use all sorts of reactions that we've covered so far in the course to be able to get from the starting product to the ending product. Now, on exams and things like that in Chem 3570 or 3580, your professor will give you a list of appropriate reagents that you can use, and it'll be your job to remember what type of reaction each set of reagents does. But in this course, since there's no list, we'll just assume that we can use any type of reaction or mechanism that we've covered already. So the first thing that I like to do for synthesis problems is to carefully look at the starting material and compare it with the final product that we're asked to make. And if we do that here, it appears that we have to substitute this CN group for this alcohol. So thinking back to the two reactions that we've just covered, does anyone have an idea for how we might be able to start this problem? Well, one idea that I have is that you can use our substitution mechanism from before with HX, whereas HX just stands for any generic halogen. And we can substitute the alcohol for that X, be that chlorine, bromine, iodine, something like that. We talked about how you can protonate the alcohol and perform an SN2 reaction and do substitution that way. So this is what we would be left with. And then, does anyone have an idea about how to go from this intermediate, or I guess in this synthesis problem, it's an intermediate, but to go from this molecule to our final product?
Hey, Sydney, do you want to try reloading that screen? I think the bottom is cut off a little.
I'm sorry, you said the problem is cut off?
No, it's good. The bottom of it was cut off, but don't worry.
Oh, sorry about that. Thanks for letting me know, Sam and Nadia. I appreciate it. I totally didn't see from my end. Alrighty. Well, to get from this substitution product to this product, we can actually react this molecule with some NaCN. The CN minus is derived from the weak acid HCN, The sodium is a spectator ion and the CN is negatively charged, and it's a pretty good nucleophile since carbon does not like to have a negative charge. So very unstable, very good to use. And we'll perform another sequential SN2 reaction to wind up with this final product. So basically, from start to finish, we start with this alcohol, we do an SN2 reaction after we protonate the alcohol to turn it into a good leaving group, and then we do another SN2 reaction to convert the chlorine, iodine, or bromine to a CN. Are there any questions about this problem or synthesis problems in general? If there are no further questions, I'm going to go ahead and turn things over to Samantha.
Thank you. Let me go ahead and stop sharing. All right, can everyone see this? Woo. Oh, there we go. Yes, no. I'm gonna keep going.
Yeah, we can see it.
All right. So Sydney was talking about how to make an alcohol into a good leaving group, like we talked about earlier. We're going to be talking about 2 different ways to do that, in addition to what Sydney already said. So one way is going to be using tosylates. Another way is going to be using mesylates. They are kind of similar processes, so we're going to go through both. But we talked about qualities of good leaving group earlier, and we noted that good leaving groups tend to be stable after they have left. So let me write that down. We want our good leaving groups to be stable. And so tosylates and mesylates are going to be 2 pretty stable leaving groups. I'm going to go ahead and give you a few seconds to think about why, and I will tell you. All right, so looking at the structures of these guys, tosylate in particular, I think is a good example. You can probably imagine that they're going to have quite a bit of resonance. 1, with that sulfur there, and then 2 for tosylate with that benzene ring. You can imagine, maybe these double bonds could shift over, that kind of thing. So one reason they're going to be good leaving groups is going to be because of resonance. They're better able to bounce that negative charge around the molecule. And so next we're going to be talking about the different reactions we can perform with them, where we convert the alcohol to either tosylate or mesylate. So the mechanism for both tosylation and mesylation are going to be kind of similar. I'm going to go through both of them. I'm going to go ahead and abbreviate tosylate. So remember, this is what tosylate looks like. I'm going to put an R for this entire group. So I'm going to draw it like this. So imagine we have some sort of substrate with an alcohol. And draw in tosylate. This is actually going to be tosyl chloride, TSCl. Note that it looks a little bit different from this guy. Really, the main difference being that you don't have that chloride over here on the side. And so what's going to happen is that the lone pairs from the oxygen on the alcohol are going to go and attack the sulfur. When that happens, it's going to pop off that chlorine. You're going to get something like this. Oops. This entire structure. Remember, chlorine is still out here, that chloride ion. That's actually going to come and deprotonate what we have just added. And so overall, it's going to look like this. I'm just going to abbreviate it. Remember, this OTS is just the abbreviation for tosylate. OMS is the abbreviation for mesylate. And so this entire structure is what we just added on instead of the alcohol. Note that we have the O for the OTS because that O came from the alcohol. Any questions so far? I'm not seeing any. Awesome. So next up is mesylation. Again, we often use mesyl chloride to add on that mesyl instead of the alcohol. So let's go ahead. Note that I'm putting a methyl here instead of that R group because there is no benzene ring. There is our mesyl chloride. Same deal, lone pair from the oxygen on the alcohol. Oops. On to that sulfur, pop off that chloride. It's going to look like this. Wow. Positive charge on that oxygen, like usual. This is going to be methyl instead of an R group. Looks like this. Cl minus. I think you guys know what's happening by now. Deprotonate, deprotonate. And we're going to be left with, oops, this guy. This being the mesylate part. Any questions so far on what I've just showed you? Okay. Let's keep on going. So now I'm just going to go over a couple characteristics of tosylation, mesylation. Basically, it's important to note that when you're creating a tosylate or a mesylate, you're not going to cause the stereochemistry of the molecule to change. So let me just draw out an alcohol. Let's do this, why not? If you had something like this, tosylation, mesylation doesn't really matter. Let me do mesylation. Remember, OH gets replaced with OMS. Go ahead and look at the previous slide if you want to remember what the MS looks like. So note that alcohol started on a wedge and this mesylate ended on a wedge, right? So same stereochemistry, no change there. If, for example, you were to then do a SN2 reaction, then of course you can get a change in stereochemistry. Let me just show you that. Let's say we had OMS, say we had the same guy as before. Let's add NaCN. Remember, NaCN is going to be good for SN2 reactions. Oops. In that case, oops, that is not that. There we go. You would go from being on a wedge to being on a dash. Remember, that is going to be inversion of stereochemistry. But the tosylation or mesylation itself does not invert stereochemistry. It always keeps the same stereochemistry. All right. Now we're going to be moving on to a few practice. This will be a shorter lecture. So first off, let's say we had this molecule in this pentagon with the carbon chain and an alcohol in here. Let's say we want to tosylate it. You can go through the entire mechanism if you want. I think you guys are good with it by now, so I'm just going to draw this. Remember, does stereochemistries change or does it stay the same? It is going to stay the same. So wedge on the alcohol, wedge on the OTS. Let's go ahead and say we wanted to do a second reaction with this OTS, so go ahead and draw him over here. Let me draw him with this pen. Let's say I wanted to do NaCN, and let's go ahead and do it with DMF. Remember that DMF is going to be a polar aprotic solvent. NaCN is a pretty good nucleophile. So these things together are going to suggest that we have an SN2 reaction. Feel free to review that lecture you want a refresher on how we know that, let me go ahead and draw that again. Pentagon. Pentagon gets worse every time. Anyway, here we go. We have our CN added there, now on a dash instead of a wedge. So like we just talked about, like you guys know, this is going to be inversion of stereochemistry. We'll give you a few more seconds to write that down. Let me move this away so I can see if they have questions. Awesome, looks like everyone is good. Okay, next practice. Again, alcohol, that's the entire lecture. Hexagon, some other carbons. There's alcohol up here. Let's go ahead and do some mesylation. Redraw your hexagon. Leave this, nothing's changing there. OMS instead of that alcohol. Remember, keep the wedge, same stereochemistry. Now let's go ahead and draw it down here for number 2. Now that we know what the first product looks like. All right, what are we doing with this guy? So NaO to ET, and I'm going to add an additional heat as well. So we have sodium methoxide. You may recall that this is going to be a strong nucleophile and also a strong base. So that plus the heat, remember that heat is going to favor elimination reactions, in this case E2. And so one thing we want to recall is for an E2 reaction, we want to take the anti-hydrogen. Let me write that in. You want to take the hydrogen anti to the leaving group. So let's look at this carbon. What hydrogen is there? It's going to be on a wedge. We can't use that guy. Let's look at the other carbon adjacent to that leaving group. There's going to be a hydrogen on a wedge and a hydrogen on a dash. So this guy, the one on the dash, is going to be the one that we take, meaning that the double bond is going to end up right here. So that is what our structure is going to look like. Any questions on those 2 practice problems? Awesome, I'm not seeing anything. Last practice, crazy looking guy. Once again, alcohol. Let's do some mesylation. Gonna redraw that benzene ring. Let me go a little bit slower. Remember, the OMS is going to be on what? The wedge or the dash. You guys know this. No change in stereochemistry is going to be on the dash. Let me just write it kind of funky like that. You know what? I'll do this. Make it easier on us. Okay, let's see what happens when we add CH3OH to him. Same structure as before. Let's look at CH3OH. So you may remember this is going to be a polar protic solvent. Polar protic. That's a polar protic solvent. So that's going to be favoring what? In general, SN1 and E1s. If, for example, we had heat here, then E1 would be favored. But remember, we're going to essentially mix the SN2 and the E2s. Here's our structure. What is an SN1 and an E1 product going to look like? Remember, for the SN1, let me draw it out first. Got all these guys. We're putting them on the wrong side. We're going to have OCH3 instead of that OMS. Remember, when you have SN1 products, you're going to have enantiomers. So let me draw its enantiomer. OCH3. Remember, these are the SN1 products. What is the E1 product going to look like? It's going to look something like this. This is going to be our E1 product. Remember, now we're going to take one of the hydrogens from here, creating that double bond. That is our E1. Here are our SN1 enantiomers. And that is the end of this lecture. Sydney and I will be sitting here for a few more minutes as usual. So if you have any questions, feel free to ask. Otherwise, you're free to go. Everybody have a good Monday.
Thank you.
Thank you.